Hi, my name is Scott. I'm from the Economics Tutoring Center at Arizona State University. Today we're going to be summarizing different statistical distributions. Please just check everything I say with your professor because notation or language use may vary. But essentially I'm going to go over a few important details of the most commonly used distributions in Econ 221, just a basic statistics course. So for each distribution, I'm going to tell you what type, meaning discrete or continuous. I'll tell you the mean, variance, PDF, which is the probability density function, or sometimes called the probability mass function for discrete distributions, and the CDF when it's not too complicated, which is the cumulative distribution function. So to start, we have the binomial distribution. This is when you have a certain number of trials. So let's say n trials. I'll write this. Each trial has probability p of being a success. So the binomial distribution is relevant when you want to know the probability of getting a certain number of successes from a certain number of trials. Now, first of all, this is a discrete distribution. Because it's counting the number of successes, it only takes on non-negative integers as values, so 0, 1, 2, etc. It has a mean of n times p, and this one's somewhat intuitive, so if you think you do 100 trials and there's a 25% chance of a success in each trial, you might expect 25 successes, and that's just number of trials times probability. So that's the mean of this distribution. The variance with an e on the end is equal to n times p times 1 minus p. So now it's the number of trials times the probability of success times the probability of a failure, because each trial is either a success or failure. Also, success and failure don't always mean good or bad things. It's just a matter of yes or no, that type of thing. And now the probability density function of this takes on this form. So you have n choose x. So this is the choice function times p to the x, 1 minus p to the n minus x. And if you don't already know, this choice function can be expanded. So it's this fraction of all these factorials, so more compactly written this way. And so if you want to know, for example, the probability of getting 5 successes out of 10 trials with a probability of 0.7, you'd plug in n equals 10 trials, p equals 0.7, probability of a success, and then x would be 5. You want to know the probability of 5 successes. Now for the CDF, for now, I'll just write that it's complicated. And by that I mean there's not a nice looking function that you can write down to describe it, but you can use the CDF in programs like Excel or in TI 83 or 84 calculator. So that sums up the binomial distribution. Next we have the Poisson distribution. Now this is also discrete. It's used to count the number or find the probability of a certain number of events occurring within a certain time frame. So if you know on average how many calls a call center gets every hour, you can find the probability that they get 3 calls within the next hour, something like that. So it's discrete because again it counts the number of events. There's no fractions or anything. The mean of this distribution is given by a parameter, lambda. And all that means is maybe the mean's 5, then lambda equals 5. You'd usually be given that if you're working with the Poisson distribution. The variance in this case for the Poisson distribution is actually also equal to lambda. So every Poisson distribution has the same mean and variance. And then the PDF is given by f of x equals lambda to the x times e to the minus lambda over x factorial. E is just a constant, about 2.7, that you can find in your calculator. Lambda, again, is the mean, and x is the value you're interested in. So, for example, you can find the probability of exactly 3 calls within the next hour by plugging in x equals 3. And of course, you have to know what the mean number of calls is. And again, the CDF is pretty complicated for the Poisson distribution, so I can't write it down. But that tells you most of what you need to know about the Poisson distribution. Next we have the normal distribution, which is the typical bell-shaped curve that a lot of people are familiar with. Now this is a continuous distribution. In fact, it takes on all real numbers as values. So all the way down to negative infinity and all the way up to positive infinity, it can take on fractions, irrational numbers even. It's defined for all real numbers. So it's continuous, not discrete. And then the mean is a parameter, so it's usually written as mu. And the variance is also a parameter, so usually we write sigma is the standard deviation, so variance is just standard deviation squared. Notice of particular importance is the standard normal distribution, which has mean 0 and standard deviation and variance 1. This is the distribution you encounter when you are working with a normal distribution and you find a z-score. That standardizes it, so you have this mean and variance. Now for the probability density function. It's fairly complicated, but it can be written down. Okay, so this is the probability density function for the normal distribution. You probably won't work directly with this very often, but it can be good to know. And then again, I know by now you're really eager to see a CDF, but these first 3 are pretty complicated, but it's coming. So this is the normal distribution. Good one to know. Next we have the exponential distribution, which is another continuous distribution. It can take on fractions and decimals as values. Where the normal distribution could take on negative values, the exponential distribution is only non-negative values, so 0 or positive values. But it is continuous. Its mean is given by 1 over lambda. Lambda is just a parameter for the distribution. You may want to be careful. Sometimes the mean is given not as this reciprocal, but just as beta, for example, without a fraction. But I think this is the more standard way. The variance is 1 over lambda squared, and notice it's the square of the mean, meaning that the mean and standard deviation are the same for the exponential distribution. And then the probability density function is then given by lambda times e to the minus lambda x. So if you want to know how dense is the exponential distribution function at a certain value of x, this is what you'd use. Now, usually what's more of practical use for the exponential distribution is the CDF. So here it is, the moment you've all been waiting for. 1 minus e to the negative lambda x, and you get this by integrating the PDF. But what this can tell you is, if you know on average, say how long it takes for a pizza delivery service to deliver a pizza, then you can set that average equal to 1 over lambda, find lambda, and then if you want to know what's the probability that your pizza arrives within 16 minutes, you plug in 16 for x, and this will tell you that probability. So, assuming the pizza delivery times follow the exponential distribution, which is important. And, right, so that's the key information for the exponential distribution. we have one more we're going to go through. It's the uniform distribution. It's arguably the simplest one. It's a continuous distribution, and it's defined by an upper and lower bound, say A and B. Probability density function, as we'll see, takes on the same, it's a constant between those values of A and B. So if you have A and B as your upper and lower bound, so what this looks like, something like this. This is the probability density function of a uniform distribution between A and B. The mean is, you'll notice, the midpoint between A and B, which is not too surprising. The variance is a little trickier. This one's just good to know. I don't have much of an explanation for it. And then the density function, PDF, is given by 1 over b minus a. Now notice that this is a function of x, but x does not appear on this side. And that reflects exactly the idea that the density is constant between these values of a and b. So this is only really defined for x between a and b. Outside of a and b, maybe to the left of a or the right of b, the density is 0. And then the cumulative distribution function, and what that would look like, let's say we want the probability of getting a value less than this x. That would look like this area here, and geometrically you could represent that by x minus a over b minus a. And again, this is only valid for x between a and b. If x is less than a, the cumulative distribution function is 0. If x is past b, it's equal to 1 because it's the probability of getting something less than b is equal to 1. So again, these are the major distributions you'll be using in a basic statistics course. And you can always just go back in the video, pause, and look at these, write them down, listen to the video again if you need practice, and check out our other videos for some more detail or examples. I hope it helped, and if you have any other questions, feel free to ask your instructor or come into the tutoring center. Thanks.